All right, so what we have here, unfortunately, gets cut off a little bit by my settings, but that's just something you're going to have to put up with. So here we have the cold, the medium, and the hot spectra. Okay, and up top, where it gets cut off, it says UV, visible, and infrared. Okay, so that's talking about the different colors of the light. The visible spectrum is the rainbow-looking dark bar there in the middle. To the left, it has ultraviolet. Okay, that's on the other side of blue. And then on the right, it has infrared. That's on the other side of red. Okay, and, thus in the middle, you have the rainbow going from red to blue. Red on the right to blue on the left. Roy G. Biff, right? All right, so this black line over on the right, it says classical theory. Okay, so that's the model they came up with based on their assumption that light behaves like an ocean wave. The vertical axis on this is just intensity, amplitude. Okay. All right, so the classical theory is this black line, and you'll notice that it doesn't behave like the three actual lines. Okay. Instead, it starts out low, like they do, way over on the right, and then as you come up on the left, it gets higher and higher and higher, and then just never ever comes back down. Okay, that was called the ultraviolet catastrophe. Okay, because as you're going from red on the right, you're coming over toward blue, and then ultraviolet on the left, it just goes to infinity. It never comes back down. And that's a catastrophic failure of their model, thus ultraviolet catastrophe. Now, the way math works, math is it's logic. So you have your assumptions up on the top. Then you have you just follow through step by step, line by line of your math until you get to some conclusion. Now, if your assumptions are good and your math is good, then your conclusion will be true. Okay. So math or logic, same thing. It can be wrong up here. If the assumptions are wrong, it's then it's said to be unsound. If your math is wrong, then it is invalid. Okay? So those are the two ways you can go wrong. You can just be wrong about the world and your assumptions. That's an unsound argument. Or you can get your math wrong, you can get your arguments wrong. That's an invalid argument. So a physicist came along at the end of the 19th century, and he took a look at what the physicists were doing. He looked at their math. He said, okay, your conclusion is garbage. Either your argument is invalid, or it's unsound. So he looked, like the rest of them did, he looked at their arguments. He looked at the steps they took to get from the assumptions to the conclusions, and he saw that those were good. Okay, so give them a check mark there. Their argument was valid. It was not an invalid argument. Okay, so if your conclusion is wrong and your logic is valid, then obviously the problem is in your assumptions. You have an unsound argument. So he said, all right, I have an unsound argument. Obviously, light is not like an ocean wave. It behaves like a wave, but it is a different kind of wave from an ocean wave. What he said was, all right, it's different in some way. Now, what they had done was they had assumed that the energy is stored in the amplitude of the wave, and that energy is, continuously variable. Meaning, you can have any energy, in between 0 and, infinity, okay? Infinitely variable. What he said was, okay, maybe it's not infinitely variable, okay? He just started playing around with the assumptions, and this is one he eventually came up with. Playing around with assumptions like, what if reality was different in this way? That's a valid way of doing physics. Okay? That's the way theoretical physicists do their research. Okay? They play with the constants of reality and see what results they get. So this is what he did, and he said, okay, what if it's not continuous? What if energy only comes in discrete units? In other words, what if it is quantized? Okay. So this comes from Latin. Quant just from quantum. And that just means count, a countum, a thingy. So if it's quantized, then it comes in individual units, just individual bits, pieces, discrete items. Okay? They're separated from one another. They're not all the same. Okay, so he said, what if energy is quantized? And when he did that, he got the right answer. So this is the result he got. Okay? The yellow bit, that is the sunlight at the top of the atmosphere. The red bit is sunlight at sea level. Okay, and then that black line, it may be hard to see, that is the prediction, okay, for 5,250 degrees Celsius. So very, very hot. That, by the way, is how they know the temperature of stars, is by measuring the spectrum like that, by seeing how what light they give off and comparing it to this model. And it works really, really well. The reason there's differences is because, even stars aren't perfect emitters of radiation. But this is the answer he came up with, and as you can see, it is really, really good. People didn't accept this right away. They thought, either he got lucky, it was just a fluke, or maybe quantum was sort of like the field, electric fields or magnetic fields. Maybe it was, a formalism that helps us understand and get to the right answer, but isn't necessarily something real. He was kind of bitter about this. His name was Max Planck. And in fact, he said at one point that science progresses one funeral at a time. He was very German. That's a very German way of putting it. As the old, powerful people who control the academies die off, then younger people with newer ideas can fill their positions. And thus science happens. But, even he wasn't entirely sure that this was real. So what happened was they had another experiment. That was blackbody radiation. This is the photoelectric effect. And the photoelectric effect. Basically, if you have a piece of metal and you shine light on it, lambda nu to represent light, then what can happen is you can get an electron flying off. That's E minus. Okay. All right. Sometimes you shine light at a metal. That's photo, from Latin photus, meaning light, and then electric for electron. So you shine light at a piece of metal. Sometimes you'll get an electron flying off. And that electron will have some amount of kinetic energy. Now, the classical conception of light, it said, remember, that energy was based on amplitude. So if you increase the amplitude, then you should get electrons with higher kinetic energy coming off. Now, that's not what you actually saw. You shine light on a piece of metal, okay, you don't get higher kinetic energy with increasing amplitude. Instead, what happens is it's based on frequency, okay? Below a certain frequency, here, let's go ahead and clear that off. Okay, so below a certain frequency, at low frequencies, you get no electrons, none at all coming off the metal. And above that frequency, okay, you do start getting more electrons. Okay, so this is high frequency. So above that frequency, you do start getting electrons, and that's when the kinetic energy will start to increase. Okay? Increasing amplitude increases the number of electrons. Not the energy of the electrons, just the number of the electrons. So classical physics, the classical understanding of light being like an ocean wave, couldn't make sense of this. Okay? But it turns out that this new idea of light being quantized can. So, one of the things that came out of the blackbody radiation model, quantum, was this constant. Okay, sometimes when you're playing around with math, Just the way calculus works, you get random constants showing up. They're just needed to sort of balance the math, right? So this is now known as Planck's constant. And it's the letter H. And it's named after, the guy who did that work in blackbody radiation. And it is 6.626 times 10 to the negative 34th joule seconds. Okay. It's there to, balance out the math. Like I said, it's very, very small. But this guy who was working on blackbody radiation, he looked at the units here for Planck's constant, and he saw that it's joule seconds. Okay. So, if you multiply h, Planck's constant, times nu, frequency, that's joule seconds times 1 over seconds. Remember, the units of frequency are hertz, or 1 per second. Then the answer, is going to have units of joules. In other words, the energy of a quantum of light is based on the frequency of the light. It's not based on the amplitude, according to this model, according to this understanding. And that matches perfectly with what they had observed there in the photoelectric effect. Okay? Because remember, low frequency, no electrons, high frequency, higher kinetic energy electrons. Okay? Because, obviously, the electrons are going to be bound to the metal with some amount of energy. They called that the work function, phi, work function. Okay. So you have to put in some amount of energy to pull the electron away. I mean, if the electron wasn't tied to the metal, then it would just fly off any old time. Okay. So below that energy, okay, you can't pull the electron off. That's why there's this threshold frequency. Okay. You need to have enough energy to get the electron off. And above that frequency, you have E equals h nu. The individual photons, individual packets of energy, the individual quanta of light, have enough energy to pull the electron off. And the higher their frequency, the higher the energy of the electron. Not only that, but now we can understand amplitude. It's not really the carrier of the energy. Amplitude tells you how many photons there are. Okay. More photons is in a way related to energy, okay? Because each individual photon carries some amount of energy. So in, a higher amplitude, more photons, there's more total energy. But each individual photon still carries the same amount of energy. Okay? That's why increasing the amplitude doesn't necessarily start kicking off electrons. If the individual photons don't have enough energy, it doesn't matter how many of them there are. You have to have enough energy in the photon itself in order for it to work. And then, once you get past this threshold, okay, increasing the amplitude will increase the number of electrons, so long as, the individual photons have enough energy.